Edexcel IAL Unit 1 Physics January 2024 paper will be discussed in this video. See the description of this video. All the necessary and useful links are given. By using the playlist of this channel, you can access any video related to physics or mechanics in mathematics. So by using the playlist, you can uh, uh, access any video related to either in physics or mechanics. All the physics lessons are classified or grouped into different 6 groups, like unit 1 lesson, unit 1 past paper discussion, unit 2 lesson, unit 2 past paper discussion, and so on. In mechanics, the videos I discussed past papers, and the relevant theories are discussed when I discuss the questions related to a particular topic. Okay, first question MCQ. Which of the following is an SI unit for stress? We know stress equal force over area, force divided by area. Unit of force, SI unit of force is Newton. SI unit of area is meter squared. So the unit of stress is Newton per meter squared. I don't need to write and explain. There's nothing to explain that. So correct answer, question number 1, D. The last answer, D. Right. Question number 2, which row of the table only contains vector quantities? It's like a IGCSE type question. Okay, vectors means they have both magnitude and direction. They should obey the vector addition rule. So the vectors are acceleration is a vector, momentum is a vector, weight is a force, force is a vector. So the correct answer for question number 2, A. That also A. So question number 1, answer D. Question number 2, answer A. Question number 3, I'll work it on the board. A spring is stretched by applying a force of 3 Newton. The elastic strain energy stored by the spring is 0.04 joules. Which of the following expressions gives the extension in meters? Okay, so question number 3, elastic strain energy is given by half F delta X given in the data sheet. So the energy is given 0.04 half times the force is 3.0 times delta X. So make the delta X subject, you will get the correct answer 2 into 0.04 divided by 3.0. So correct answer A. So question number 3, correct answer A. Okay, question number 4. A cyclist moves along horizontal road at a constant speed. She then moves at the same speed up a hill with constant gradient. So the slope is constant. So initially the cyclist is moving on a horizontal floor along horizontal road. Then constant gradient means the slope is constant. So the cyclist initially moving here, then moving here, climbing like this. Right, okay, whatever it is. Which of the following graphs shows how the power output? So power is equal to, we know that force into speed. So it's moving at constant speed. That's power output. So power output, the following graph show how the power output P of the cyclist. So the cyclist is still working. The cyclist is doing work because maybe due to overcome the friction force. So when you apply force and when you do work, when you pedalist, actually it would have accelerated, but it's not accelerating because the force you need to apply the moment you are creating on the pedals is same as the opposing friction. So that's the reason the cyclist is transferring power, but it's moving at constant speed means the F is the friction that is opposing the motion. So it's moving at constant speed. Right. So when it is moving at constant speed on a horizontal floor, the power, how the power will vary with time. If I draw a graph, power against time. When the cyclist is moving at constant speed and constant force he has to apply, a cyclist moves along horizontal at constant speed. She then moves at the same speed up the hill with constant gradient. Which of the following graph shows how the power P of the cyclist varies with time? So he is moving at constant speed means no resultant force, because if there is resultant force it would have accelerated. But there is work done by the cyclist to overcome the resistive force. So because otherwise there won't be any power output from the cyclist. So the cyclist is doing work. So cyclist is applying a force equal to the total resistive force, the friction. Okay, so it's moving at constant speed. How do I know? They are telling it. The force he is applying also constant. So power is constant. So the graph will be initially when he is moving on a horizontal floor, constant power. Right. Now when he is climbing on a slope which has constant gradient, it's moving at the same speed, but the force he needs to apply now will be more, because the component of the weight also going to act this way, mg sine theta. Then the same friction what it had earlier also will be there. So the force the cyclist has to apply will be more, but it's constant. The force becomes more because the component of the weight also opposes the motion, but he is maintaining the same speed, but the force has increased, so the power output will be more. The cycle has to develop more power. So, but again it's a constant power because constant force, constant speed. So the graph should be constant force, constant power. Suddenly it increases when it climbs on the slope. This is the graph. Okay, so answer D. Okay, question 5. A student dropped a tennis ball, table tennis ball. The ball fell for time t and had velocity v just before it hit the ground. The student used the equations of motion to calculate t and v. T is the time taken and v the speed. These equations ignore air resistance. Which row of the table shows how the actual values compared with the student's calculated value for the t and v. Right, okay, so imagine student is dropping the ball from a particular height h. Initially the speed is 0 because the question says dropped, not thrown. So dropped means initial speed will be 0. Normally, if there is no drag force, the student assumed there is no drag force. So actually when we consider the acceleration, the actual forces acting on it are the weight and the drag force. We assume the drag force is constant. Okay, normally we know the drag force changes with time, but we assume the drag force is constant for simplicity to get an expression. So the resultant force acting on the ball, mg minus fd. Normally, if we assume there is no drag force, Fd will be 0. F equal ma, so A is equal to mg minus Fd over m. Right. But normally, when we consider the questions, normally we assume the drag force not exists. So if mg becomes 0, so acceleration becomes, and when Fd becomes 0, acceleration will become mg minus 0 over m. That will be g. Normally we take like that when there is no drag force. But here they are saying actually there is drag force, but the student thought there is no drag force. So the acceleration student considered in his calculation, it as g, but practically the actual acceleration, mg minus fd, you are subtracting a particular quantity. Actually we should subtract a particular quantity, which is the drag, divided by m. If fd, student assume there is no drag, so he got acceleration g, but here there is a drag force, so actual acceleration will be smaller than g. So actual acceleration actual is smaller than g. It won't be same as g. Okay, student calculated the speed. What could be the time taken to reach the ground? He calculated. So he would have used s equal ut plus half at squared. Anyway, the height is h. Initial speed 0 because it said dropped. So initial speed 0, half times a, he would have put g t square, and he would have got t as 2h over g, all things square root. Right. But I told that actually the acceleration is not g, that is smaller than g. So if the acceleration becomes smaller than g, the actual equation will be Instead of G, we should put T is equal to square root of 2H over A. A is this one which is smaller than G. So A means A actual. This ACTI stand for actual. Okay, leave it. A less than G. If there is drag force. So the time is going to be, this is small. It's going to be smaller than actual value, means the time actually will be more. It will take more time. It will take more time than the student, how much he obtained through calculation. So the time, actual time is going to be longer. Right. Then he calculated the final speed. Say, to calculate the final speed, he would have used V equal U plus AT. U is 0. A, I already told, actually A will be smaller than G. Student would have used G, but actually acceleration is smaller than G. So this is smaller than G. Or we can use, or we can use V squared equal U squared plus 2S. That's equal, easy. V squared equal U squared plus 2as, that's easy because time won't come there. So this is 0, 2 times. He would have used a as G, but here the a is going to be smaller, a, h. So a is lower, actually a is lower than G. So the final speed will be, actual final speed will be lower than what he obtained. Actual time will be greater than what he obtained. So time will be greater and the speed will be less than calculated. Answer C. Correct answer C. You might ask, why can't we use, when we analyze the final speed, can't we use V equal U plus AT? No, it's not a suitable equation. V equal U plus AT if I use, I accidentally wrote it and I change it to V squared equal U squared plus 2S, because if I'm using this one, anyway U 0, right, actual A is smaller, is it? So actual A is smaller. Actual A is smaller, we know that. Actually A is smaller than G. The time is going to be larger than larger than time calculated by the student. So the actual time is larger, actual A is smaller, one quantity is smaller, other quantity is larger. When you multiply both, we can't predict the outcome. Will it be more or less? A is going to be smaller than G. Okay, student used G, but I know actual A is smaller, so A should be smaller. The time what student compared to the calculation of time by the student, actual time is larger, we know that. So time is larger, smaller. When you multiply both, we don't know the outcome V, will it be larger than the student's calculated or smaller? We can't say, because one is larger, other one is larger, other one is smaller, we can't say. So that's the reason I choose equation which does not have time. So V squared equal U squared plus 2as is the correct equation or suitable equation to analyze or compare the final speed with the student's final speed value. Okay. Okay, question number 6. A length of string is attached between two vertical posts. A bird of weight W stands on the middle of the string, causing tension T in the string. The string makes an angle 80 degree with each post. Means, so the diagram is given like this. So here there is tension, here there is tension, here the bird is sitting, the force exerted by the bird, the push by the bird is equal to its weight W. These angles are 80 degree given. Mean if you draw extended line, alternative angle, this will be 80, this also 80. When you resolve T upwards, T for the equilibrium of the bird is at rest. So the total vertical force must be equal to 0. So T cos 80 plus T cos 80 minus W equals 0. So 2T cos 80 equal W. So T will be W over 2 cos 80. Answer C. Question 7. Okay, so force is applied to stretch a spring. The graph shows how the Length of the spring varies with applied force. Length of the spring. Which of the following gives the stiffness of the spring? So length or whatever it is, length or extension, the graph is going to be a straight line. But the only thing is, when the applied force becomes 0, if it is a graph of force against extension, uh, when the applied force becomes 0, the extension becomes 0 if the spring is within the elastic limit. The graph will be a straight line through the origin. But if the graph is force against length of the spring, when the force becomes 0, there will be, the graph will cut the x-axis. That's going to be the natural length, initial length of the spring. But both graphs will be parallel to each other. Both graphs will be parallel to each other. So if you find the gradient here, or if you find the gradient here, both will have the same gradient. According to F equal k delta x, the gradient will give the spring constant. So the question is, which of the following gives the stiffness? Stiffness means spring constant. Stiffness of the spring, that is the gradient of the graph. Correct answer C. So that is for the question number 7, answer C. Right, question number 8. A solid cube of weight W is made from material with density rho. Which expression gives the length of each side of the cube? So density equal mass, you know that density equal mass over volume. Mass is equal to weight over G. Weight over G, or we know that weight equal mass times G. Okay, volume for a cube, that is equal to L into L into L cube. So if you multiply length into width into height, L cube. So simple, use them. So density is going to be, instead of mass we can say W over G over L cube. Okay, so we need to get expression for length. So L cube is going to be W over rho G. L is going to be cube root of W over rho G. So answer D. Okay, question number 9. Two graphs are given. I am not drawing it. You can see the paper. A force is applied to stretch two wires P and Q until the wires break. So the last point of each graph gives the breaking stress or breaking strain, the last point on the graph. So that is question number 9. Difficult to draw exactly the same graph. So something like for P drawn like, yeah, for Q, this is for P. Q is drawn like something like this. This is P. Not exactly the same, but yeah. So this is stress and this is strain. Right. Which of the following statements is correct? P has greater breaking stress than Q. You can see that. That's wrong. Q has the greater breaking stress. So that statement is wrong. Breaking stress is more for Q. Right? Then P has greater breaking strain than Q. That also you can see the strain is more for Q. Yeah. Then we'll go to the D part. P has lower Young modulus. Actually, P has higher Young modulus. Young modulus is given by the slope of the straight line part or gradient of the straight line part. So, which one has greater gradient in the linear portion? P. But the statement says the D, statement D, P has lower Young modulus is a wrong statement. So, we know A, B and D are wrong means they are not correct statement means answer C is the correct one. P has greater yield stress than Q. Yield point means beyond that point, for smaller change in stress, there will be larger change in strains. Try to find that way beyond the elastic limit. Somewhere here difficult to draw, but you see that one of the type of MCQ answer you can eliminate and get the answer, right? So here we know that answer A, answer B, answer D, we know 100% they are not correct, means answer C should be the most suitable or correct answer. Okay. Okay, question number 10. An object moves from rest, so the initial speed is 0, with uniform acceleration for time t. So during time t, it's moving at uniform acceleration, but how much is it not given. The acceleration time graph for the object is shown. X is the area. So this X is the area under the graph between time 0 to t. So this area is X. We know that. The area under the graph of acceleration time gives the change in velocity. So when you are answering this type of question, you must know the properties of the graph. If you are dealing with distance time graph, gradient gives the speed, or displacement time graph, gradient gives the velocity. But area covered by the graph and the time axis for speed distance time graph, it does not have any meaning. But if you think about speed time graph, the speed time graph, the gradient gives the acceleration. Area covered by the graph and the speed time graph, area covered by the speed time graph and the time axis gives the distance moved. Same way for velocity time graph, the slope or the gradient gives the acceleration. Area covered by the graph and the time axis gives the displacement. For acceleration time graph, the property we deal is the area covered by the graph. Area covered by the graph gives the change in velocity. We can do that way, but another way also they will tell that. So we know that change in velocity equal area. So change in velocity means it's accelerating at constant acceleration A. We don't know the A, it's not given for time t. So the velocity changed from 0. It was initially at rest, the question says. So the change in velocity, final velocity minus initial velocity is equal to the area. So V is equal to X. The question is, which of the following expressions give the distance moved by the object during this time? So that we can use. We know the final speed is. So I know the initial speed 0. So I can use the equation S equal U plus V by 2 into t. So u is 0, v is x by 2 into t. So if you solve it, you will get s is equal to half xt or xt by 2. So answer D, correct answer D. Or you can do this way also. You know the acceleration is a. We don't know, the a is not given, but we can take the acceleration is a. So if the acceleration is a, the area is x is a into time, the second method. This is method 2. This is method 1. Either way we can do. So a into t, that's acceleration into time, because the graph is a rectangular graph. So a into t is equal to x. So t is going to be x over a. Then you can use s equal ut plus half a t squared. So we know that initially, t equal x over a, but I want to get a is equal to x over t. A is equal to x over t, because a is the unknown quantity. So s equal ut plus half a t squared. It's moving from rest half. Instead of a, I can put x over t. This is into x over t into t squared. Solve it. T squared. So it's going to be xt over 2. Same answer you get it. Okay, whatever the method you can follow. Any of one of the method you can follow. Okay, question number 11. A student applied a force F to a rubber band. The student measured the corresponding extension delta x, and F was increased and then decreased. So that we call loading, unloading. F increase is called loading, F decrease is called unloading. The graph shows how delta x, that is extension, varies with F was increased and then decreased. A part, state how the graph shows that the rubber band deformed elastic. I didn't draw actually what is the graph given there. I just drew a random graph. But the A part state how the graph shows that the rubber band deformed elastically. What do you mean by elastic deformation? Elastic deformation definition means when the applied force is removed, if the material returns to its initial shape or original shape, that's called elastic deformation. So here, when you remove the applied force, how do you know the material is returning to initial shape, or how do you know the material is coming back to the initial shape? Means the extension should become zero. So see the graph. The upper graph that is called increasing force is the loading graph. You are applying a force, so it's extended. Now the graph drawn below, that is decreasing force, means you are removing the force. Finally, the decreasing force becomes zero. It's passing through the origin or reaching the origin. So when the force becomes zero, extension also becoming zero. That means there is no permanent deformation. There is no permanent extension. That means it has returned to the initial shape. That means it is within the elastic limit. So the question is state how the graph shows that the rubber band deformed elastically. You can say that when the applied force is removed, the extension of the rubber band becomes zero. That means it has returned to its initial shape, or it has returned to its original shape. That's the answer for A part. B part, calculation, question number 11, B part. The work done on the rubber band as F increased is greater than the work done by the rubber band as F was decreased. So you can see that, this topic we normally teach. We can use the equation for work done or elastic strain half F delta X. But we say that that equation is correct if the force against extension graph is a linear graph. If the force against extension graph is a linear graph, we can use this equation. But even for metal wires, if the extension passes beyond the limit of proportionality means the point up to which the force is directly proportional to extension. If the graph goes beyond the limit of proportionality, and if they ask to find the work done or energy stored at this extension, there you can't use this equation, because this equation is valid only when the force is directly proportional to extension. Or you must remember that this equation we can use only when the material is within the limit of proportionality. Whether you are using F equal half W equal half F delta X or half K delta X squared, both same equation, but these equations are applicable only when the material deformation is within the limit of proportionality. Otherwise, we have to find the area covered by the graph and the extension axis, not this area covered by the graph and the extension axis. That area we have to find it. Okay, whether the deformation is within the limit of proportionality or beyond the limit of proportionality, no problem. We can find the area between the force and between the graph and the extension. That will give the energy stored in it, elastic strain energy stored in it. Okay, the whole equation we can use only when the material obeys up to limit of proportionality. Okay, so here you can see the graph, what is given there. The increasing force graph has larger area between the graph and the extension, but decreasing graph has small area. I just sketched the shape of the graph. This is the force, this is the delta X. So the increasing force graph is something given like this. No, not exactly the same. Yeah, it's like something like this. Yeah, this is increasing force. The decreasing force graph is something like this. Okay, so you know that area covered by the graph and the extension axis gives the energy stored in it or work done. So this area, that is during loading, the area is more, unloading, the area is less. So we know that this area, see my video, I give the link for the video I uploaded for solid material. So this area is the heat loss, because you are doing more work when you are loading. When you are unloading, when you are removing the applied forces, this graph has small area below this. So this amount, what it means what's the physical quantity represented by this shaded area, that is the heat dissipated to surrounding. This behavior is called hysteresis for polymers, right? So the question here, there is a difference in these two values because heating occurred. Yeah, there's a heat dissipated to the surrounding. So there's a difference between this area and this area. Determine the energy that caused and heating F was increased and then decreased. So we need to find the area of this graph in SI unit. So force should be in Newton, exertion should be in meters. If I find this area, that's the energy, heat dissipated to the surrounding. Okay, how to find the area of a curve? Okay, so we use a method. We count the number of squares below the graph. For example, that only I drew this graph. Actually, this graph is not the given graph. Just I took a example. How to find the area covered by the graph and the time axis. Graph and the extension axis. To find that, we take this way. This one square indicates which consists of tiny 5 squares. You know, there are scales are shown on the grid. So the one division I took it, one division here on the x-axis, one division means that consists of tiny 5 squares. Same way, the division of each division on the y-axis, that also consists of tiny 5 squares. That 5 into 5 square is taken as one division, right? So there you can, when you consider this division, the graph, the blue color graph is covering more than half of the square. Is it? Starting from here, if it reaches this edge, then we will say it's covering only the half. But the graph is little above. I am again saying this graph is not the given graph. I just drew a graph to explain how to find the area. So here this graph is more than half of the square. If it is more than or equal to half of the square, we take it as one full square. That's the way it's a method, right? One full square. So actually it's not one full square below the graph when we consider this square, but we take it as one because it's covering more than half of the square. So we'll take it as one, right? So this also, this square is completely below that. So that is 1, 1, 1 is all are below that one. But when you consider this square, the second, this square, the graph is passing here. We know that the area covered by the graph inside this square is less than half. Because it's entering from this side but leaving here. So we can, eye level, we can see that this is smaller than half of the square of the graph. So we take it, if it is less than half falls within the graph, we take it as 0. No area is taken. We take it as 0. But when you consider this square, here it's more than half, so we'll take it 1, 1, this also 1, 1. Again, this is 0 because it's less than half is covered. 0. This is 1 because more than half is covered. More than half, this full square, so 1. This is more than half because entering from here 1, right? So how many total squares are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 squares are there. So area covered by the graph equal 13 square into area of a square. Area of a square. That's the way we find the area covered by the graph and the x-axis. It's a method actually, right? So in that way, in this question, you need to find the area or number of squares. Area means first we'll find the number of squares below this graph. If you count it like this way, 1, 1, 1, 1. If it is less than half is covered, we should take it as 0. So like that, if you count the number of squares below this loading graph, I got 42 squares are there. Below that graph, 42 squares are there. Slightly it might vary for different students. The number of squares below this graph, the unloading graph or decreasing force graph, in which I counted 20 squares are there. For me, sorry, 22 squares are coming for me. So what is the number of square between these two graphs? 42 square minus 22 graph, that is going to be 20. So area between area of the shaded portion, so area of the shaded portion is the heat lost to the or heat dissipated to the surrounding. That's the question they asked. So area of the shaded portion is 42 squares, that is here, minus 22 squares into area of a square. Area of a square you have to give it in SI unit. So 1 square, that consists of 5 tiny squares I told, that is here 10 tiny squares marked as 1 centimeter. So that's going to be half a centimeter. So 0.5 into 10 to the power minus 2 into y-axis 0.5 Newton. That is the area of 1 square. Solve it, you will get the final answer. So that is going to be 0.05. This is Newton, this is y-axis is Newton, x-axis is meter, so joules. That's the energy dissipated to the sun. That's the final answer. Okay, question number 12, it's based on projectile. In a game of called darts, metal darts are thrown towards a dartboard. The darts hit the dartboard as shown. A dart is thrown with a velocity of 15.6 meter per second at an angle of 5 degrees to the horizontal. The dart travels a horizontal distance capital D to a dartboard as shown. Just before the dart hits the dartboard, the vertical component of the velocity of the dart is 0. So vertical component becomes 0 means the dart is at its highest point of the path. Okay, so only the vertical component becomes 0. It's going to bend down after that. Anyway, but here this is the projectile path. It follows a path like this. So here the board is there. So this is 5 degree. So initial speed is given 15.6 meter per second. So this distance is d. Okay, so the question is here the velocity is 0. At this point, the vertical component VV, vertical velocity is 0. They are telling it. Okay, so air resistance is negligible. Show that the time taken for the dart to reach the dart board is about 0.14 seconds. So what's the time taken by the dart to reach this point from here? So that's we can use, decide which equation to use. So we know the final speed, which is 0. We know the initial vertical component of the speed, that is going to be 15.6 sine 5. So v equal u plus 80 we can use. In vertical direction. So vertical velocity here 0. Initial vertical velocity 15.6 sine 5 plus A is going to be the acceleration, is going to be downwards 9.81 meter per second square. I am using upward direction. So I am taking any quantity upward positive because these are vector equations. So any quantity upward I took it positive. So u, when you resolve it vertical, it's pointing up. I wrote it with positive sign here. We don't put positive sign normally, but it's positive sign, is it? If you don't put the sign, that means it's positive. So the acceleration is downward. So I should put minus 9.81 t. Okay, so solve it. That is, this is going to be 15.6 sine 5 minus 9.81 t. So bring it to the left and find for t. You will get 0.139. Give it in 3SF. 139 seconds. Second part, that is B part. This is A part. Now B part. The question. Calculate the horizontal distance d. So simple. You use horizontally. S equal ut plus half at square. That is d equal initial horizontal component of the velocity 15.6 cos 5 into the time we found it here 0.139. Horizontally, no acceleration, because acceleration is vertically down. The gravitational acceleration is vertically down. So if you want to find the acceleration horizontally, you have to resolve it horizontally. So when you resolve a vector through 90 degree, it won't have any component. So the acceleration in horizontal direction is 0. Solve it for D, you will get 2.16 meters. Okay, question number 13 is based on Archimedes principle, the floating, right? Student has a toy called Cartesian diver. So the Cartesian diver means actually the tube. This is a tube. There's a bottle which consists of a tube, upside down tube. Inside there is air and water is there. So except it's like a test tube, something like a test tube, something like a test tube. So the water is outside also water. So it's there like this. So water is around it. This portion consists of air, right? So the whole thing is called Cartesian diver. The Cartesian diver consists of tube closed at one end, actually upper end. Air is trapped by water inside the tube as shown. The student squeezes the bottle, so maybe a plastic bottle. Yeah, it is squeeze the bottle. You can push more water inside. Means when more water goes inside, the amount of trapped air will decrease. Right. So more water is forced into the tube and the volume of the trapped air decreases. Explain why Cartesian diver accelerates downwards. Okay, now we'll see. Now before you squeeze, when it is at rest at this position, something like that. So it consists of water outside, but this is air. This portion is air. If you think about the forces acting on this upside down tube, how many forces acting? The tube itself should have a weight. The tube has its weight. So the weight will act downwards. So the weight of the tube is acting down. So, but this water which is inside won't part of the tube. The water can go up or down. But when you consider this, because outside also there is water. Outside also there is water. So if the tube is not there, imagine if the tube is not there, this whole region must be occupied by the water which is outside the bottle. So bottle is here. This is the bottle. So if there is no tube, the whole region will be occupied by the water. But because of the tube, only this portion where they mark it as A, this portion is occupied by the air. So that portion of water where air occupies, that portion of water, that volume of water is displaced. Is it? Because we don't consider the thickness of the material of the tube, we are not considering. The material of the tube has weight. The material of the tube has weight, but the thickness of the material we don't consider. Nothing mentioned about the thickness of the material. So the tube itself is not displacing water. The tube itself is not displacing water. We don't know anything about that. But the air, inside the tube, a certain portion of air is trapped. That air is displacing certain volume of water. That water has weight, because the amount of water displaced by this air, it has weight. You know how to find it. Volume of the displaced water into density of water into G. That is the weight of the displaced water. According to Archimedes principle, that is going to be the upthrust on the tube. That is going to be the upthrust on the tube. Is it? So there, how many forces are acting on the tube means the tube has two forces. One is downwards weight, and the other one is upthrust. Why there is upthrust? Because of the displaced water, and which is the displaced water is occupied by, that region is occupied by the air. So because of the displaced water, there will be upthrust. Upthrust will be upward, weight is downward, both should balance each other. So when you consider the equilibrium of the upside tube, the weight must be equal to upthrust. Weight must be equal to upthrust. Right? You can try just like if you fill in a small, in a big open water tank or big bowl, you keep a small cup upside down, this is filled with water. and you keep even a metal cup, hold it upside down and try to immerse it, you will feel the upthrust because of the water inside the cup. In the cup, when you push it into the water, so there is air. When you bring this cup and you try to immerse it upside down, what will happen? A certain portion of the cup inside air will be compressed, so water might occupy here. You will feel the upthrust. When you hold it here, you will feel the upthrust. Why? Because of the displaced water. Displaced water, which water is displaced? Where the air occupies this region, this is air, no, still there. So that amount of volume of water is displaced. That displaced water has weight, that causes the upthrust according to Archimedes' principle. So here there is upthrust because of the displaced air. Right. So weight is equal to upthrust when the tube is at equilibrium. Now when you squeeze the bottle, they are saying when you squeeze, more water enters to the tube. That sentence is there. The student squeezes the bottle, more water is forced into the tube. So more water is forced into the tube means earlier like this. So when more water forced into the tube means the water might go up to here. Now what's happening? The volume of the trapped air is decreasing, but weight of the tube remained the same. There's no change in the weight of the tube, but the volume of the trapped air is decreasing. The volume decreases. Weight upthrust is equal to volume of the trapped air into density of water into G. Now volume of the trapped air is decreasing means upthrust will decrease. When the upthrust decreases, the weight remains same as earlier. So upthrust earlier balancing. Now what's happening when the volume decreases? When you squeeze the bottle, more water pushed in. More water pushed in means that volume of the trapped air decreases. When the volume of the trapped air decreases, weight of the displaced water is decreasing, upthrust is decreasing. So now what's happening? Weight is acting downwards, upthrust is acting upwards, upthrust is decreasing, weight remains the same, means there will be a resultant force downward direction. So according to Newton's second law, the tube will accelerate down. That's the answer you should say. This is the answer for question number 13. Okay, question number 14. This diagram is given. A child's slide has a vertical height of 1.7 meter as shown. It's a curved path. A child starts from rest at top of the slide and moves down the slide. The resistive force acting on the child can be ignored, so no friction. Explain why the equations of motion should not be used to determine the maximum speed of the child. Okay. Now normally the conditions to use equations of motion, first it should move on a straight line, then the acceleration should remain constant. These are the two conditions to use. But if the slide is a straight line, something like this, there we can use the equations of motion. If the angle of slope is theta, when the child slides, I will draw the child as a small sphere like this, small dot like this. So if the weight of the child will act vertically down, if there is no friction, there will be normal reaction. These are the two forces acting on the child. The component of the weight along the slope down will be, you know that when you resolve this weight along the slope, it will become mg sine theta. Remember that, that is mg sine theta. So if there is no friction when it moves along the slope down, if I use F equal ma along the slope down, F is equal to mg sine theta, because the normal reaction won't have any component along the slope, because the normal reaction is perpendicular to the slope. When you resolve the normal reaction through 90 degree, it won't have any component along the slope down. So the only force acting on along the slope is component of the weight along the slope, that is mg sine theta. So it's going to be mg sine theta equal ma. So A is going to be g sine theta. That's the acceleration when the child slides along a straight slope when there is no friction. Okay, But if the angle varies at different points, if the angle varies, that is, if the slope varies at different points. The question says the child starts from rest at the top of the slide and moves down the slide. The resistive force acting on the child can be ignored. Explain why the equation of motion can be used. Determine. Okay, so the diagram is clear. It's not a straight line. So if the angle of slope varies at different points, the theta varies. Say for example, if it is something like this way, the slope is something like this. If the angle of slope varies, then what will happen? Theta will vary. When the theta varies, acceleration will be different at different points. So we can't use the equation v squared equal u squared plus 2as or p equal u plus at. Any of these equations we cannot use because a is varying at every point. Okay, so the conditions to use the equations of motion, it should move on a straight line, first condition, then the acceleration should remain constant. So it's just 3-mark questions. So the answer you have to say, first you can say the conditions to use equation of motion, it should move on a straight line with constant acceleration. Then you can say the slope of the slide is varying at different points, therefore component of the weight along the slope will vary, and hence the acceleration will be different at different points. Therefore, the equations of motion cannot be used. So this is the answer. Question number 14, A part. Okay, so second part. This is A part, first part. This is A part, first part. A part, second part. The child has a mass of 24 kilogram. Determine the maximum speed v of the child on the slide. So on the diagram, the vertical height the child has moved along the slope is 1.7 meters. So we can't use the equations of motion. So the only option is we have to use the energy equation. Okay, energy equation means when the child moves from top to bottom along the slope, the child is losing gravitational potential energy, and according to law of conservation of energy, it's gaining kinetic energy. There is no friction, so no work done against friction. So the only two energies are involved in loss in GPE, that is loss in gravitational potential energy, equal gain in kinetic energy. Gain in kinetic energy. So actually the mass of the child is not necessary here because it's going to get cancelled on both sides. Loss in GP mgh equal gain in kinetic energy half mv square minus half mu square. Gain means final kinetic energy minus initial kinetic energy. All the mass will get cancelled. So 9.81 into the vertical height. H is the vertical height through which it moves down. So that is 1.7 meters equal half v squared minus, the child is moving down from rest, the question says, so 0. Find the v. The speed at the bottom, 5.77 meter per second. Okay, so B part of question number 14, these two different slides are given. Both have no friction. Two slides X and Y have the same height. So they have the same initial height. So the height is same, h. So the child is going to slide from here. So a child is going to slide from here. So when the child reaches the bottom, if I draw the child like a small sphere, when the child reaches the bottom, the vertical height the child moved down will be the same on both slides. And both slides there is no friction. But there are, in this question, there are two different children. They are sliding. The slide X is longer than slide Y. The longer means you can see the length of slide X is longer. So this length is smaller, this length is long. If I say this length, the total length it moved down is dx. This length to move down is dy along the slope. This dx greater than dy. The length of the slope is, length of the sliding is longer for X. A child moves from rest down slide X and reaches maximum speed Vx. So a child X is moving from here, and when it comes to the bottom, the maximum speed is Vx. There's another child Y is moving along the slope. When the child comes to the bottom is Vy is the maximum speed at the bottom. The child on Y has greater mass, that is My, mass of the child on Y greater than mass of the child on X. But both has no friction, the length is different, height is the same. The question, the resistive forces acting on the child can be ignored. The child Y has greater mass than X. Explain how Vx compares with Vy. Okay, nothing. Anyway, we can't use equations of motion because it's not a straight line. So we have to consider in terms of energy equation. So when the child X moves from X to Y, the top to bottom, the loss in GP for that child, is mx gh. That is the loss in GP. For this child, my is my gh. Okay, so both have same height. Mass y greater than mass x means loss in GP is greater here. Loss in GP is greater here for the child in y than the child in x. But no friction. So we are going to use the same earlier equation. What is it? Loss in GP equal gain in Ke. So loss in GP, generally if I write without considering the x or y, generally if I write loss in GP mgh is equal to half mv squared minus 0. So here whatever the mass they have, whether mass y is greater than mass x, whatever it is, for a child if I write, for a particular child if I write the energy equation, the mass will get cancelled. Already we got it in the first part. The mass will get cancelled. So GH equal to half V squared. So V is going to be square root of 2GH. So both have the same height. Both are falling through the same height. But they are traveling different distances. They are going to travel different distances. So height is the same. They are traveling different distances. But the final speed is going to be the same. Okay, because the reason, even if they have different mass, you should say the mass will get cancelled. So that's the answer you need to give. So you should say according to energy equation, loss in GP equal gain in Ke. You should write this one. Then write the proper format. Generally, not for X, not for Y. Generally you write it. Then you say the mass M. I didn't write it. I'm going to write it. The mass will get cancelled. Then you show V is equal to square root of 2GH. Then say, since both are falling through the same vertical height H, at the bottom, both Vx and Vy will have the same magnitude. That's the answer you should tell. Okay, right. This question, just the answer. Both will have the same maximum speed. Where will it be the maximum speed? At the bottom. If you want, you can say both will have the same maximum speed at the bottom. Vx equal Vy. It's okay. Right. But this question could be modified like this also. This answer is correct. It's over. Right? But I just want to discuss a little more. Now, in case if the question says the same condition, the length dx greater than dy, mass of the child on y is greater than mass of the child in x. But if they say both slides have the same friction, both slides exerts the same friction on exert same friction, if they say both have the same friction, here they are saying ignore the resistive forces acting on both children can be ignored. But in case if they say both children experience the same friction, that also could be there. Both children experience same friction. In case if they say which one will be larger or will they have the same value, the maximum speed Vx, Vy, will they have the same value? We'll analyze it. Okay, so there, because of this one, the energy equation will have a slight difference. We will say loss in GPA, there loss in GPA equal gain in KE plus work done against friction. Loss in GPA equal gain in KE plus work done against friction. So question says no friction. I am just analyzing if there is friction, what could be the answer, right? So when the child moves down, is losing the GPE, gaining kinetic energy, but all the loss in GPE won't become gaining KE because a certain amount or certain fraction of the loss in GPE will be converted to work done against friction and will become sound and heat, right? Okay, so loss in GPE, mgh, gaining KE, half mv squared minus half mu squared, but u is 0. Work done against friction, friction force into D. I am writing generally D. I didn't put dx, dy. I didn't put in masses also mx or my. Generally I am writing. Then we'll think about separately what could be the outcome. What could be the speed finally. Okay, so we'll rearrange this one. So u is equal to 0 anyway. Initial speed 0. Both children are falling from, sliding down from rest. So when u becomes 0, you will have mgh minus, bring it to the, okay, equal to half m v squared plus frp. Bring it to the left, that is mgh minus fr is the friction, frd equal half m v squared. Sorry, yeah, here m will not be get cancelled because the friction has no mass. So earlier this was not there, we were able to cancel them, here we can't cancel them. So we will make the v squared subject, cross multiply by 2, you will get 2mgh minus 2frd equal mv squared. Okay, so I need to analyze it further. V squared is going to be divided by m, the whole equation, you will get 2gh minus 2 frd over m, right? Now we'll take about the square root, but anyway I'll keep it with v squared. If you want I can write with square root. Is equal to square root of 2gh minus 2 frd over m. Now I have to give the final conclusion. Now you can see for both slides or for both children, this quantity 2gh is the same because both are moving, falling through the same height. So this quantity is the same for both. On the right side, minus this quantity, fr is the same, friction is the same. When you consider the slide y, dy is smaller than dx. So numerator has a smaller value, dy smaller than dx. So numerator is smaller. When you think about the mass, my greater than mx. So denominator is becoming larger. Numerator is smaller, denominator is larger for y when you consider. Now if you think about x, dx is larger, numerator becomes larger, dx. Mass of x is smaller, denominator becomes smaller. What will happen for a fraction, say a over v fraction, when a becomes, when I consider y, the child y, for the child y, dy is smaller, so a becomes smaller, b becomes larger, because mass of the child y is larger, so a becomes smaller and b becomes larger, means this fraction will become smaller. A becomes smaller when I think about y, d becomes smaller, dy is smaller than dx, but mass of y is greater than mass of x. Numerator smaller, denominator larger, means A smaller, B is larger, means this fraction will become smaller. When this fraction becomes smaller, we are going to subtract a smaller value from 2GH. Therefore, Vy, we are going to subtract smaller value for y. Therefore, Vy will become greater than Vx if there is same magnitude of friction. In case if they ask, this is the answer you have to give. Okay, question number 15. A student investigated small ball bearings falling through a liquid to determine the viscosity of the liquid. State the conditions. A part, state the conditions. State the conditions needed for Stokes' law applied to this investigation. So normally, generally the Stokes' law, to use Stokes' law, the conditions, the object should be a spherical shape object and the fluid flow around it should be lamina. That means speed of the motion of the fluid around the object or relative to the object, the sphere, the fluid flow should be lower, then only the flow will become laminar. But here they are saying ball bearing, so it's going to be anyway sphere. So they say state the conditions need Stokes' law to be applied. Answer A, part A, you should say. The fluid flow around the sphere should be laminar. Therefore, it should have a lower speed, because when the speed increases, mostly the laminar flow will become turbulent flow. So the answer you should say, the sphere should move relatively at lower speed, then only the fluid flow around it will become laminar. Okay, that's the answer you should say. I'm not writing, you know that. Okay, B part, first part. Complete the free body force diagram for a ball bearing when falling at terminal speed. So B part, first part, terminal speed means the resultant force acting on it is 0. So when it is falling down, it will have two forces upward. One is up thrust, other one is drag force, downwards weight. But it's moving at terminal speed. Terminal speed means the resultant force is equal to 0. So total upward force should be equal to total downward force. Total upward force equal to total downward force. So we are going to draw a free body force diagram. Means in free body force diagram, the length of the arrows should represent the magnitude of the forces. So we know total upward force equal to total downward force means eye level, when you add the length of the two arrows you are going to draw upward, one is up thrust, other one drag. You can put FD here, you can use U. Must be equal to weight means if you add the length eye level, that should be equal to weight. So that means the length of weight should be longer than both these, each of those two upward forces. Right. Now second part, there's a calculation. Okay, so that is second part. This is B part, first part, B part, second part. The student thought that the liquid she used might be glycerol. She made measurements to determine terminal velocity of ball bearing. The terminal velocity of the ball bearing was 0.0824 meter per second. So that the student measured. So it's a data. We know she measured the terminal speed, which is 0.0824 meter per second. Deduce whether the liquid used was glycerol. The other data, the density of the glycerol is given, radius of the ball bearing given, weight of the ball bearing given, viscosity of glycerol at room temperature given 0.934. So that is the actual value of viscosity of the glycerol. So other things are density of the glycerol also given 1.26 10 to the power 3. Okay, so here what will we do? We don't know whether the liquid is glycerol. The density is given for glycerol. The terminal speed what she measured is given. So there we can do like this. We assume we don't know the glycerol's density. The viscosity of the glycerol is unknown. So we'll find the viscosity of the glycerol and compare it with the value they have given. They have given in the question. If both are almost same, we can say the liquid they used is glycerol. Okay, so here they are not asking you to calculate any quantity. The question is deduce whether the liquid used was glycerol. So we'll find the coefficient of viscosity of glycerol if it wants to have the terminal speed which was measured by the child, which is 0.824, to have that terminal speed, and if it is falling in the density of 1.26 10 to the power 3 kilogram per meter cube, that is the density they are giving it in the liquid, we'll check whether the viscosity satisfies the actual viscosity of the glycerol. Okay, so the equation is here. The resultant force is 0 because the terminal speed is given 0.084, means terminal speed, the speed at which the resultant force becomes 0. So the at terminal speed, we can say the total weight mg minus upthrust minus drag force equal to 0, no resultant force because it's moving at constant speed. So mg is given, upthrust is equal to, so we'll write again mg, upthrust is equal to, we know that we have to find the volume of the sphere. So anyway, we need to find the volume of the sphere, upthrust, V, density of the glycerol, E rho g. Okay, the volume is the volume of the sphere, that's the volume of the displaced liquid, V, density of the liquid which is glycerol, they are saying it, and G minus 6 pi eta R Vt equals 0. Okay, so we'll find the volume separately. If you want, you can find the volume separately, or you can find it here. I think it's better to find the volume separately. Volume is equal to 4 by 3 pi. The given data is radius is given 4 by 3 pi r cube. We'll find that one. So that's going to be 4 by 3 pi r cube. Radius is given as 2.3 millimeter, 2.30 10 to the power minus 3 all in cube. So find it. So that's going to be 5.097 10 to the power minus 8 meter cube. That is the density, sorry, that's the volume. Okay, we'll substitute these values. mg is given weight of the ball bearing in 4.00, 10 to the power minus 3, volume 5.097, 10 to the power minus 8, density of the glycerol, that is the liquid, 1.26, 10 to the power 3, minus upthrust, that's upthrust, drag force 6 pi, eta we are going to find it, radius again, that's given, radius is 2.3, radius is given 2.3 millimeters, so 2.3 10 to the power minus 3 into the terminal speed also given, that is 0.0824 equal to 0, so into 0.0824 equal to 0 at terminal speed, what I wrote here. Okay, now rearrange it and find the, only the unknown is eta, the viscosity. So solve this one, is going to 4 into 10 to the power, that is if you solve the left side, 3.37 10 to the power minus 3. Solve others, to the take it to the right, this quantity take to the right, so that becomes 3.573 10 to the power minus 3 eta. Find the eta, you will get 0.934 Pascal second. So the actual value of eta is 0.934. This okay, we got 0.943. 943. Actual value is 0.934. So conclusion, you can say, if you want, you can find the percentage difference, but that's normally we do for unit 3. But you can say, since this value, the calculated value of the viscosity of the liquid is very closer to the actual value of the glycerol, therefore the liquid is glycerol. You can give the conclusion. Okay, question 16. A skittle is a wooden object that can stand upright on an end. In the game of skittles, a ball is thrown at some skittles to knock them over as shown. Okay, so the diagram below shows the ball just before it collides with the skittle. The graph is given how the velocity varies with time in milliseconds during the collision. The graph is given. Determine the average acceleration. Don't try to find the gradient or slope of that straight part, because that is the acceleration during that time. So they ask you to find the average acceleration, means just before collision what's the speed? It was 0. Finally, what is the speed? You can get it from the graph, that is the final speed will be 2.85. Okay, so at the time taken from the graph, just the graph is like this. It's something like it's a straight line, then its graph is turning like this. So find the time from here and here. Okay, the speed, this is the final speed. This, the slope of this one will give the acceleration during that time, but they are asking for the average acceleration, means average acceleration compared to initial final speed we had to consider. Initially it was at rest, finally what's the speed? That is this speed, this is the final speed. So we have to get the time, how long it takes for to change the speed from 0 to that particular value. Okay, so average speed v minus u over t. From the graph, if you get it, 2.85 minus 0 over 48. This time read it 48 millisecond. 48 minus, this is 15 where the 0 is start to move. 15 10 to the power minus 3. So that average acceleration will be 86.3 meter per second. Okay, explain how Newton's second and third laws of motion apply to the ball and the skittle during the collision. So it's like this, second part. This is I wrote for A part. Now B part. B part I need to answer. Okay, so the ball is moving. This is the skittle. This is the ball. So during collision, before collision, the skittle was at rest. After collision, during collision, it's going to experience force in the direction of motion. So it's going to experience force this way. The ball was moving this direction before collision u. During collision, the ball is going to experience same magnitude of force according to Newton's third law, opposite direction. So just before collision, the ball had velocity towards left. During collision, the force is going to be opposite to the direction of motion. The force experienced by the skittle and the ball will have the same magnitude according to Newton's third law. They will be in opposite direction. Therefore, now according to Newton's second law, this is the only force acting on the skittle. So the skittle will accelerate from rest. But the ball is experiencing unbalanced force, resultant force opposite to the direction of velocity. Therefore, according to Newton's second law, the ball will decelerate. Whenever object experiences a resultant force opposite to the direction of motion, according to Newton's second law, it will decelerate. So the ball is going to slow down because it's experiencing force opposite to the velocity just before collision. But the skittle is going to accelerate because it was at rest. This is the only unbalanced force. It's going to accelerate. That's the answer you should say. This is the answer for question number 16, B part. Okay, so question number 16, C part. The ball is thrown again and collides with another stationary skittle. During the collision, the horizontal velocity of the ball changes from 7.2 to 1.3. You can see the velocity is dropping, decreasing, because the force experienced by the ball during the collision is opposite to the direction of its velocity. So it will decelerate. You can see it's dropping from 7.2 to 1.6. The horizontal velocity of the skittle immediately after collision is 3.1. It was at rest, now it's accelerating 3.1 in the same direction as the ball. Determine the mass of the ball, mass of the skittle is given. So we can use law of conservation of momentum. So before collision, mass of the ball we don't know, velocity was 7.2, the skittle was at rest, so mass into velocity 0 for skittle before collision. After collision, mass of the ball is m remaining same, the velocity is same direction as earlier, so both positive, same direction, 1.6. The skittle also moving in the same direction, so that also will be a positive quantity. So mass of it is 1.4 into its velocity 3.1. Solve it and find the m. So that is 7.2 m minus 1.6 m is going to be 5.6 m is going to be 1.4 into 3.1. Find the m. You will get 0.775 kilogram. 3SF, better give the answer. Okay, question 17. A student determined the Young modulus of a material in the form of a wire. The student used a micrometer to measure the diameter of the wire. Describe how the student should check the wire is uniform. So, to check whether the wire is uniform, measure the diameter at many different points along the length of the wire. Okay, they're asking how can you confirm the wire has a uniform diameter. That's the thing, check that the wire is uniform. So to measure, to check whether uniform diameter does it have, measure the diameter at many different points along its length. Next point, how can you check that the wire has a circular cross section? So if it has not circular, it might be slightly compressed or somewhere. So measure the diameter at different orientation. Keep the micrometer screw gauge like this, then rotate it and keep it. Then you can measure here, rotate it and keep it. So measure the diameter at different orientations, several different orientations. Rotate the micro wire and measure its diameter at different orientations at different points, different orientations at different points. Okay, so if they are not same, the wire is not wire does not have uniform cross section or uniform diameter. It might not be a uniform cross sectional is not uniformly circular. It might be something else, or it might be pressed somewhere. Okay, those answers are the answers for the A part. B part, the student hung the reference wire and the wire being tested from the ceiling. So they are using the Hooke's law apparatus, vernier caliper, those all are given, the diagrams all are given. And they are saying vernier scale has 0.0 millimeter initially, 100 gram mass is attached. So that is B part. First part, the student kept his feet away from the apparatus so that the masses could not fall on his feet. Explain one of the safety precautions. So normally you can say this, the string or the wire might snap, therefore wear safety goggle. So explain. State means you can say wear safety goggle. Explain why should I wear safety goggle. You have to tell, explain, careful. The answer for explain and answer for state. Right here, explain means you should say the wire might snap or break, therefore to protect the eye, wear safety goggle. That's the answer for B part, first part. B part, second part. Each time the student added more mass, delta x increased by few millimeter. Explain why he should measure delta x using vernier scale instead of meter rule. So actually they are saying it's increased by few millimeter, maybe 1 millimeter, 3 millimeter, something like that. Few millimeter it is increasing. So few millimeter means you can use even meter roll, because resolution of meter roll is 1 millimeter. If the increase in extension is 3 millimeter, you can use either vernier caliper, this Hooke's law apparatus, or meter roll. But why vernier caliper is the best? Hooke's law apparatus consists of vernier scale. Why do we need vernier scale? You should say The resolution of the vernier scale is smaller, therefore the reading will have smaller uncertainty and hence smaller percentage uncertainty. Again, I am telling it, I am not writing it. The vernier scale has resolution of 0.1 millimeter. Therefore, the uncertainty will be 0.05 millimeter, and the percentage uncertainty, that's a very important, percentage uncertainty of the measurement will become smaller. Percentage uncertainty will become smaller. You should tell about the resolution, 0.1 millimeter for vernier. For, if you want, you can say the resolution for meter rule is 1 millimeter. This is 0.1 millimeter. Vernier caliber 0.1 millimeter, meter rule 1 millimeter. So we know that resolution is smaller for vernier caliber or vernier scale. Then you should say the uncertainty will be 0.5 millimeter for vernier scale. Therefore, percentage uncertainty will become smaller. Right. Now part C, a graph is given. Y-axis is delta x extension. Normally we draw y-axis force, x-axis extension, but here y-axis is delta x in millimeters and x-axis is force in Newton, and it's a graph slightly cutting the x-axis, something like this. They have given the graph. Okay, so the graph here, it's not passing through the origin, but it's not an issue because the value is cutting force axis is almost 0.75 Newton, but it could be a systematic error, or maybe the extension cannot be measured for this small force. Actually, the graph should be a straight line through the origin. If I draw a graph parallel to this one, that will be a straight line through the origin. Okay, we can find the gradient. We don't need to take just one point and do the calculation. If it is passing through the origin, it should be the same gradient. So we know that Young modulus is equal to tensile stress over tensile strain, that is force over area over extension over original length. So we'll rearrange this equation because it's a straight line. So we'll rearrange this equation. So it's going to be E is equal to Fx over A delta x. We'll make the delta x subject because it's on the y-axis. So delta x is equal to F over EA into x over EA into F. So this is in the form of y equal mx format. By taking two clear points on the graph, that's advantage of one of the advantage of graph, we can remove the systematic error, right? I mentioned that in the unit 3 video. The advantage of plotting graph, we can remove the systematic error. So take the gradient of it. So if you find the gradient from the graph, take two clear points. The gradient will be equal to I took these 2 points, 7.8 minus 2.2 10 to the power minus 3 millimeter to meter over 11.5 minus 4, this much of meter per Newton. So the gradient, that is m, becomes 7.467 into 10 to the power minus 4 meter per Newton. Right. So that is, the gradient is x over EA. So m is equal to x over EA. So we need to find the Young modulus. So we'll find the area of cross section separately. Area is equal to pi d by 2 squared. So separately, if you find, that's advantage, because even if this answer goes wrong, you might get marks for that. So that is pi into the diameter is given 0.17 millimeter. 0.17 millimeter to meter divided by 2 all things square. So area of cross section will be 2.269 10 to the power minus 8 meter squared. Okay, so substitute here. When you substitute here, E is going to be x over m times A. So E will be x, the length of the y is given 1.80 meter over The gradient I found it 7.467 10 to the power minus 4 into area of cross section 2.269 10 to the power minus 8. So the Young modulus you will get 106.2 10 to the power 9 Pascal. That is, the Young modulus is 106.2 gigapascal. Now check it with the table given. 106 is brass, so the answer is brass. They asked to identify the material. So in terms of Young modulus, the material used is brass. The advantage of taking gradient is we can eliminate the systematic error. Okay, question 18. A uniform door of width W is supported by two hinges X and Y. X and Y are vertical distance L apart. State the conditions needed. For the door to be in equilibrium, so that you must know if an object wants to be at equilibrium under system of forces, two conditions must be satisfied. The resultant force must be equal to 0 in any direction, or overall resultant force must be equal to 0. Moment about any point, the total moment about any point must be equal to 0. Again, resultant force must be equal to 0. Total moment about any point must be equal to 0, or the total moment about any point must be 0 could be stated as about any point the total clockwise moment must be equal to total anti-clockwise moment. That's the principle of moment, right? B part, give the meaning of the term center of gravity, O-level question, the point at which the weight of the object considered to be acting, right? Now C part is the calculation. They are giving the door, I'll draw the diagram. Okay, the C part, question number 18, the diagram is given where it shows the forces acting on the hinges X and Y. The forces exerted by the hinges X and Y on the door are shown. Sometimes friends ask why the forces are not the same direction, they have different directions. Say, for example, if you think about the door, this is the door. So its weight will act at the center, Now think like this, if the hinge X is not there, there is only one hinge Y, what will happen? Due to the weight of the door, if you think about the moment about Y, due to the weight of the door will try to rotate this way, is it? So the door will push the hinge. If you think about the hinge like this is the hinge. These are the parts which is connected to the frame, and this is the part connected to the door. The door will push the hinge. When the door pushes the hinge will push the door. That force is acting this way. So the hinge Y will push the door this way, because door will push the hinge this way, because door will try to rotate this way. So door will push the hinge to the left this way. Hinge will push the door this way. So that's the reason force exerted at Y is shown at an angle like this. Okay, now why the force acting on X is shown like this means, now think about X. Easy thing if Y is not there. Think about the moment about X. The door will try to rotate. There will be a clockwise moment due to its weight. So door will try to rotate this way. It will stretch, it will pull the hinge which is connected to the door. Now same thing if you think about X. This is the part of the hinge connected to the frame. This is the part connected to the door, means the door will try to rotate. So when the door try to rotate here, it try to rotate this way, it will pull the hinge. It will pull the hinge this way. Hinge will pull it. According to Newton's third law, hinge will pull it this way. That's the reason the two forces marked on the door by X and Y have different unusual, looks like very unusual directions. Okay, here at Y, this is the hinge Y. The door will try to rotate. and it will push the hinge, it will compress the hinge. So when the hinge is pushed by the door, according to Newton's third law, hinge will push the door in this way. When you think about X, door will try to rotate about X and it will pull the hinge this way. The door rotates this way, it will pull the hinge this way. Hinge will pull it this way according to Newton's third law. That's the reason the two forces are marked like this. Okay, so the forces won't be at horizontal or vertical direction, they will be at angle. So the total vertical force of these forces on the hinge must be equal to weight. They might be same or not, but the question says they are same, the vertical forces, right? Anyway, that's I just explained, not the question, but I just explained why the forces on the hinges are in different direction. Okay, so now the question is, the mass of the door is given 14.4 kilogram. The weight of the door causes a moment about each hinge. Showed that the horizontal component of the force of hinge Y. So I already drew and showed that the force acting on the hinge X and Y, I showed it. This is X, this is Y. So on the force exerted by the hinge X on the door will be this way. Now you know the reason. The force exerted by the hinge Y on the door is this way. So this force has a horizontal component. If I consider horizontal component, it's going to be F cos theta. Rather than saying F cos theta, I can say Fh. So the force acting on Y horizontal is Fh. This is the line of action of the force. The question is, find the horizontal component of the force at Y. That's a question. Show that the horizontal component of the force of hinge Y on the door is about 40 Newton. Okay, so we'll take moment about X. Take moment about X. Moment means force into perpendicular distance to the line of action of force. So the line of action of weight is, this is the weight, this is the line of, this is the weight, mg. So line of action of weight is this line. This is the line about which the line of action. Line of action of horizontal force at Y is this line. Right, about X we consider. So we'll consider the moment about X when we consider mg into this distance. So this is the line of action of force. Perpendicular distance to the line of action of force means we need this distance. This distance we need it. We know the width is 0.85 meter. This is the center of mass is at the center of the door. So this will be half of 0.85. So the clockwise moment, when you consider about X, the weight will provide clockwise moment. At X, the weight will provide clockwise moment. So the clockwise moment will be mg into 0.85 by 2. Now the horizontal component of the force exerted by the hinge, that I took it Fh. The line of action of force is this line. This is the line of action of force of that horizontal component. So perpendicular distance to this from X is this length. From here to here, that is 1.60. So that will provide, this will provide a clockwise moment. This is going to provide anti-clockwise moment. So still the door is at rest, means clockwise moment must be equal to anti-clockwise moment, or total moment equal to 0. I took clockwise moment 0, positive. So this will provide anti-clockwise moment. So Fh into L equals 0. Substitute. Mass of the door is given 14.4 into 9.81 times 0.85 by 2. Take it to the right side. Fh is the question, into L is 1.6. So find Fh. You will get 37.5 Newton, approximately 40 Newton. That's the question. Okay, that's the answer for the C part, first part. C part, first part. C part, second part, it says the vertical component of the force of each hinge on the door is equal to half of the weight. So here I told the forces are at different angle. if you resolve this vertical component, both will have the same value, that is equal to half of the weight, because total upward force equal total downward force. Total downward force mg, total upward force also must be mg, but they are saying they are sharing it equally, so we'll accept that half of the weight of the dough. Hinge y exerts a force F on the dough at an angle theta. So this is theta, they are saying this is theta. Okay, so determine the force F and angle theta. I need to find this F and theta. They can ask even this one. You don't need to pick at. But this question they are asking only this F and theta. Okay, that is the second part. Sorry, C part, second part. Yes, this is C part. First part I answered. This is C part, second part. Okay, so the total component of the vertical component of the force is half. Each of them are carrying half, means this is equal to the vertical component of this force is half of the weight. So F sine theta equal mg by 2. I can find F sine theta. Mg mass is 14.4 into 9.81 by 2. So that's going to be F sine theta will be equal to 37.5. That is the vertical component. This is the vertical. I can call this Fv, vertical component, upward direction force. Fv at y. At y, Fv is equal to 37.5 Newton, vertical force. We already know that horizontal component, Fh, we already found it. Fh, we found it. Fh is equal to, that is F cos theta. That is 37, sorry, I think I made a mistake. F sin theta, sorry, I made a mistake. F sin theta is F cos theta. I need to find. This is F, this is Fh. This is Fh, sorry. This is horizontal component. I already found it. Fh, that is F sin theta. Theta is measured with normal. Okay, that's a mistake. Here is the normal. Theta, right. So F sin theta 37.5. That we know that already. That is the horizontal component. Now, Fv, the vertical component, Fv is equal to, I think, I had to change everything. The theta, I put it in a wrong way. The theta is measured with normal. So, sorry, that's going to be F cos theta. Fv is equal to F cos theta equal mg by 2. So, that is 14.4 into 9.81 divided by 2. That is Fv, that is equal to F cos theta. So that will be equal to 70.6. First equation. That is Fh, horizontal component, that is F sin theta. F sin theta, that is 37.5. Second equation. Now I need to find the F and theta. This is vertical, this is horizontal. Okay, they are perpendicular among them. I can do in two different ways. First one, I can find the Fv and Fh, I know that. Fv and Fh, I know that. So divide the second equation by the first equation. Second equation, if you divide it by the first equation, F sin theta over F cos theta equal 37.5 over 70.6. F will get cancelled. Sin theta or cos theta, tan theta. Tan theta will be equal to 0.531. To solve this, 0.531. So theta is equal to 28 degree. Substitute this theta in one of the equations, you will get the F. So if I substitute in the second equation, F sine 28 equal to 37.5. So from that find the F, you will get 80 Newton. That is one method. Right, second method. We know the horizontal component and vertical component. So if we know two forces, those are in perpendicular among them, the resultant of Fh and Fv is F. is it? Resultant of FV and FH is F. So I can do that way. This is first method. There's nothing wrong. You can get the answer like this. Both I found theta and F. So the second thing, I know the horizontal component and vertical component. So the resultant of it must be equal to F. Say for example, I know the horizontal component of force, that is we found it already, that is 37.5. The vertical component, we found it as 70.6. The resultant of it must be the F. That makes an angle theta here. If we resolve two forces, then we find the resultant of those resolved components, we will get the initial force. Okay, so to find the F, we can use Pythagoras theorem. F squared equal to 70.6 squared plus 37.5 squared. Find the F. You will get the same answer, that is 80 Newton. To find the resultant, tan theta, that is equal to opposite force. That is, if you think about the vector diagram, this is the vertical force, 70.6. This is the horizontal force, 37.5. This is the F. This is the angle theta. So tan theta equal opposite 37.5 over 70.6. Find the theta, you will get the same answer, that is 28 degree. Either way you can do. Both actually the same, they're different formats. Okay, I drew the diagram for the last part. They are saying an identical door is supported by hinges that are much closer together. So the hinges are earlier, the distance between the two hinges, it said earlier question L is 1.6 meter. Now they are reducing the distance, maybe 0.7 meters, 0.5 meters, something like that. They reduce the distance between X and Y, right? But the door with the same weight. Okay, identical door is supported by hinges that are much closer together. Explain how the smaller value of L has become smaller now, affects F and theta. So the F is the force, earlier also the same F. The F is acting this way. The force exerted by the hinge Y on the door is this way. And this is the theta. How F and theta will change or will be affected when the distance between the hinges becomes smaller. Okay, we can think like this. We normally consider moment means force into perpendicular distance to the line of action of force. Imagine if the hinges are further apart. The same diagram I draw it like this. Try to draw the same length of door. The weight is acting at the center. This is the line of action of the weight. If the hinges are far apart, like this. This is X. This is Y. The force exerted by the hinge Y on the door is this direction. This is the force F. When I consider moment about X, right? We'll think about these two diagrams, figure 1 and figure 2. I'll write the answer separately. Now I just explain it. Figure 1 and figure 2, when I consider, when I consider moment about X, because I want to analyze the force acting on the hinge Y. Okay, now when I consider moment about X in both diagrams, here X and Y are closer, here X and Y are far apart. The distance between X and Y is L, maybe larger value. Here the L is smaller value. If you want, I can say L, L1, doesn't matter. It's smaller L, larger L. Okay, so the moment when I consider, there are two forces acting on the door when I consider moment about X. One is the weight, the other one is the push given by the hinge on the door. Okay, when I consider the moment of the weight of the door about X, in this diagram, that is mg into this length. This distance d is half of the width of the door, because center of mass g, that is at the center. So the center of mass is remaining the same, identical door. So the clockwise moment has no change when the hinge, whether they are far apart or closer, the clockwise movement of upper hinge X, clockwise movement about the moment about the upper hinge X that forms clockwise moment of the weight has no change, because mg into d, here also mg into d, so the clockwise moment has no change. But if the dough is at equilibrium rest, clockwise moment must be equal to anti-clockwise moment. So the clockwise moment, that is mg into d, that has no change. Whether the distance between the hinges are larger or smaller, the clockwise moment, I'll put this way, clockwise moment is the same. Since it is at rest, anti-clockwise moment also should be the same, but anti-clockwise moment, when we consider about x, that is provided by the push by the hinge y on the door. So the line of action of the force on the hinge is this one. This is the line of action of the force. The line of action means you can extend the line any amount. Then I need to consider perpendicular distance to the line of action of force from x. This is the perpendicular line. Perpendicular distance I need to consider. Same way, here the line of action of force is this one. So the perpendicular distance will be this one. This is the perpendicular distance. You can see when the hinges are getting closer, the perpendicular distance to the line of action of force F becomes smaller. When the hinges are far away, the perpendicular distance to the line of action of force will become larger. You can see the two diagrams. This is larger, this is smaller, because I am considering moment about x. So I need to consider the force into perpendicular distance. So this is larger than that. Whether they are larger or not, the moment of the force F about x must be equal to mgd. Why? It's at equilibrium. So if I say this length L generally, so L becomes smaller when xy gets closer. So F into, it's going to be F into the force F into L. L becomes smaller. This is same. Clockwise moment about the weight remains same. This is going to be the anti-clockwise moment. That must be equal to the clockwise moment. When the hinges are getting closer, L will become smaller. When L becomes smaller, the force F will become larger. When L becomes smaller, the force F will become larger. So when the hinges are getting closer, the force exerted by the hinge Y on the door will become larger. That is one answer. They are asking about what will happen to the F. Then they are asking about theta. So F will become larger. Right. Same setup they are saying. Here also the upward vertical component of the forces acting on x and y. Each force on x and y, the vertical component equal to half of the weight. We had to take that way. So that means if I consider vertical component, F cos theta equal to mg by 2. So I already showed it. When the hinges getting closer, F will become small, L becomes smaller. L becomes smaller means F will become larger. So when F becomes larger, this is constant. Mg by 2 has no change, identical though. F will become larger, L becomes smaller, F becomes larger, F becomes larger. Cos theta will become smaller. In cos theta, when the value, cos value becomes smaller, you can check the calculator. When cos value becomes larger, smaller means theta will become larger. So theta will become larger. So that's the conclusion. When the hinges get closer, the clockwise moment provided by the weight will remain unchanged. Since the door is at equilibrium, anti-clockwise moment of F about x also should be equal to clockwise moment. But the perpendicular distance to the line of action of force will become smaller. Therefore, F will become larger. When F becomes larger, the vertical component F cos theta remain the same, which is mg by 2. So when F becomes larger, cos theta will become smaller. When cos theta becomes smaller, theta will become larger. That's the final answer. This is the final answer for question number 18, part Question number 18, seed part, third part. Yeah, I hope you understood. Yeah, you can pass your comments whether you understood or not.